Functions that take trees as input or return trees as output are often tree recursive themselves. Let's look at some examples. In practice, one does not often create trees using the tree constructor and a set of explicit labels, but instead generates the tree programmatically. For example, if I want to create a function that builds a Fibonacci tree, then I would write it in the following way. If n is less than or equal to 1, that means the fib tree for that n is just a leaf. I create the leaf using my tree constructor. Otherwise, I need to build the two branches of a Fibonacci tree. The left branch and the right branch are both going to be constructed with recursive calls to fibtree. Finally, I want to return a tree. That means calling the tree constructor on some label value and the branches. The branches are placed into a list. And what about the label value? Well, here I apply the Fibonacci recurrence. I get the label of the left tree and add it to the label of the right tree. The base case of fibtree1 or fibtree0 is just a leaf. Fibtree2 has structure within it. It's the label and has two branches which are both leaves. Fibtree4 is the Fibonacci tree that we've been looking at in examples so far. So its label is 3, and then it has how many leaves? 1, 2, 3, 4, 5 different leaves. Oftentimes, we'll write functions that take in trees and do interesting things with them. Here's a not so interesting thing as a simple example. If I want to count the leaves in a tree T, I'm going to write a tree recursive function. Processing a leaf of a tree is often the base case of a tree processing function. Here, if T is only a leaf and I count the leaves, there's one leaf. The recursive case typically makes a recursive call on each branch, then aggregates the results. In this case, what we're going to do is take each branch in the branches of the tree and count the leaves in each branch. The leaves in the total tree are just all the leaves in the branches summed up. There's our first tree processing function. Let's walk through it one more time. The T comes in. I don't know if it's a large tree or a small tree. If in the simplest case it's just a leaf, then I know what to do. I just say there's one leaf. Otherwise, I sum up all of the results of making recursive calls on each of the branches. Count leaves B for B in the branches of the tree. So what's particular about the count leaves function is what it returns in the base case and how it aggregates its recursive calls. And of course, don't forget to return that result. We saw before that fibtree4 has 5 leaves. And let's make sure that our count leaves function returns 5. It does. Now, by the way, fib trees get pretty large. Fibtree10, which has Fibonacci number 10 at the top, has lots of leaves. How many leaves? Let's count. 89 leaves. An interesting fact is that 89 is Fibonacci number 11. Here's a discussion question. Implement leaves, which returns a list of the leaf labels of a tree. So how does it work? It takes in some tree, and you call leaves on it, and it gives you all the values of the leaves. So notice that the root label 3 is not in here, only the leaf labels. In order to implement this function, we're going to use a fact about sum, which is that if you sum a list of lists, you get a list containing the elements of all of the lists in the input. Let me show you some examples. If you sum the lists 1, 2, 3, and 4, you get one list containing 1, 2, 3, and 4. In order to call sum on a list of lists and have it aggregate all of the values in those lists, you have to provide a starting value of an empty list. If I sum a list with 1, I get a list with 1. If I sum a list that has 2 elements, and the first element is a list within a list, then what I'm going to get is still a list within a list in the output. Notice the difference between this structure and that structure. 1 was a value in the output. In this case, a list containing 1 is a value here. So it's not enough just to sum the whole tree and get all the labels within it, because sum doesn't remove all of the nested structure. It just gets rid of one level. Okay, here's the implementation of the tree processing function that takes in some tree and returns a list of the leaf labels. If it's a leaf, then we get the label and put it in a list. Otherwise, we sum up something. Here are 8 alternatives. I recommend that you pause and think about it. I'm going to show you the answer in 3, 2, 1. Our goal is to get a list of leaf labels for each branch and then put them all into one long list of all the leaf labels. We get that by summing a recursive call to the leaves of B for every B in the branches of the tree. So this is almost identical to count leaves, except for we have a different base case and a different use of sum, meaning a different way of aggregating the return values of the recursive calls. A function that creates a tree from another tree is typically also recursive. So for example, if I have a tree, maybe it's a Fibonacci tree, maybe it's something different, and what I'd like to do is return a new tree that has exactly the same structure, but the leaf labels have been incremented, then I'll write a tree recursive function to build the new tree. If I'm building a tree that's only a leaf, I get the label, I add 1 to it, and then I need to return a tree because that's what increment leaves does. So a quick check is that I do have the right range here. I'm returning trees just like I should. In this case, we return a leaf because we got a leaf in. If I've been given a tree that is not a leaf, then I need to increment the leaves in all the branches of that tree, and then build a new tree with those new branches. Notice that I keep the label the same, and that's because this function doesn't do anything with the labels of the nodes that aren't leaves. Here's another tree processing function, increment t, which returns a tree like t, but with all labels incremented. I'll show you a trick. You don't always need to have a separate base case for the leaves if every tree is treated the same way. This is a one-liner that says, return a tree where I've incremented the label and I've incremented all of the labels in all of the branches. This is tree recursive. How do we ever reach a base case? Well, when there are no branches, such as in a leaf, this is an empty list and we're done. We don't make any recursive calls when we reach a leaf. We didn't need to use an if statement to say that because that's built into list comprehensions, that if this list is empty, then the whole comprehension is empty and doesn't require any work to construct.